So why do some molecules react and others don't? The answer to this question lies in frontier molecular orbital theory, which helps us predict how chemical reactions occur by looking at the highest occupied and the lowest unoccupied molecular orbitals. Today, we'll apply this theory to a real example, the reaction of formaldehyde with hydroxylamine to form an oxime. Plus, I'll show you how you can calculate these orbitals using Gaussian 09 and visualize them in Avogadro. Topics we'll cover. First of all, we'll answer the question, what is frontier molecular orbital theory? Number 2, how does it explain chemical reactivity? And number 3, a real example, calculating and visualizing frontier molecular orbitals for a nucleophilic addition reaction. So first of all, in 1952, Kenichi Fukui published a paper in the Journal of Chemical Physics entitled A Molecular Theory of Reactivity in Atomic Hydrocarbons. This laid to the foundation of frontier molecular orbital theory, which led to his sharing the Nobel Prize in Chemistry with Roald Hoffman for their work on reaction mechanisms. Fukui realized that a good approximation for reactivity could be found by looking at the frontier orbitals, HOMO and LUMO. This was based on 3 observations of molecular orbital theory as 2 molecules interact. Number 1, the occupied orbitals of different molecules repel each other. Number 2, positive charges of one molecule attract the negative charges of the other. And number 3, the occupied orbitals of one molecule and the unoccupied orbitals of the other, especially the HOMO and LUMO, will interact with each other, causing attraction. So the energy gap of these orbitals determines how easily a reaction happens. The smaller the gap, the more reactive the molecules. So let's apply FMO theory to the reaction of formaldehyde and hydroxylamine. So here's how it works. Formaldehyde is the electrophile. It has a low energy, lowest occupied molecular orbital, or LUMO, that can accept electrons. Hydroxylamine, NH₂OH, is the nucleophile, and its nitrogen has a lone pair in the highest occupied molecular orbital ready to attack. If the HOMO of NH₂OH and the LUMO of formaldehyde align well, this reaction should proceed easily. Let's confirm this by calculating these orbitals using Gaussian 09. Okay, so let's model formaldehyde and hydroxylamine and calculate their energies. And let's look at that, and then let's determine their orbitals and map that out. So I'm going to go into Mo, and we're going to model, first of all, I need formaldehyde. I'm going to give it a name. Put an oxygen. I click on the bond. I make that a double. We're going to add some charges. I'm just going to do a simple energy minimization in the amber force field, like so. So now it should be energy optimized in amber. It took us about 28 energy evaluations to get there. And now we're going to set up our quantum mechanical calculation in Gaussian. I'm going to use E3LYP, 631G, and use my D option for polarization, no diffuse functions. And then we're going to update connectivity and vibrational frequencies. Now it did put this NMR in vibrational circular dichroism. If you don't want that, just go over to MOPAC, go to Gaussian. That's a little trick to get rid of that. And then so we do formaldehyde, give it a name, N-proc shared equals 6. I'm going to run on 6 CPU cores. We need a checkpoint file, so I'll give myself a name on the checkpoint file, and then view my input file. I don't need all these numbers on my checkpoint file. I'm also going to add a keyword, pop equals full. Now what does that keyword do, right? Let's take a look. And pop equals full in Gaussian. This is the population keyword. And so this properties keyword controls the printing of molecular orbitals and several types of population analysis and atomic charge assignments. The default is to print just the total atomic energies and orbital energies, except for guess equals only jobs, for which the default is pop equals full. So populations are done once for single point calculations and at the first and last points of geometry optimizations. Note that the population keyword requires an option. And so the density that's used for population analysis is the density keyword. We're not using that, so we're not going to worry about the density. Population analysis results are given in standard orientation, and so the output controlled by this is molecular orbitals and the orbital energies, atomic charge distribution, and multipole moments. So that's why we're using the pop equals full keyword. So we're going to save this as formaldehyde.com. And so that's my formaldehyde. Now I'm going to go in and do my hydroxylamine. Hydroxylamine, so there's my amine. I need to add a hydroxyl. We will fix charges. We'll energy optimize using molecular mechanics. And so, if I kind of look at this, you'll notice that all my hydrogens, if I kind of look at the Newman projection here, they're in the staggered orientation. So it does appear optimized. Of course, quantum mechanics will do that using Gaussian, but I always like to start out as close to a optimization as I can. So now we'll go to quantum mechanics and we'll give this a name. Now I need to shift over to Gaussian. I usually start at the top and work my way down. So we'll use DFT. We will set our polarization to D, 601G, no diffuse functions. We will just do that. And I'm going to use 6 processor cores, like so, and we will do our hydroxylamine, and we'll get our input file, right? We'll take away the extra numbers. We will add our population keyword, like so. And then we can save this as hydroxylamine.com. So there we go. And now I'm ready to run. So I can get out of Mo. I don't need Mo anymore. We're going to look at my com files. So I've got a few others, but here's formaldehyde and hydroxylamine. And now what I can do is I can just type, I'm going to get a program, and let's just kind of gedit Gaussian.sh. And so what this is going to do, this is a way scripting. So this gets the SH shell, and then I'm going to put my .com file. Now everything in here is just going to run as if it's running on a normal shell, but it's a program, so it's going to run that sequentially. So I just need to start off with formaldehyde.com. The nice thing about this is if I'm doing multiple runs like this, it'll run everything all at once. If I have lots of files to run, then I can set those up and set it up to run, to start it running, and it'll run overnight, and then I can come in the morning. Here I only have 2. It's not a big deal to run, and they'll both finish in less than a minute, but for the sake of demonstration, we'll do this. So my Gaussian 09 is my command, formaldehyde.com and hydroxylamine.com are my input files, and then the G98 files are my output files. Now if you're scripting, you need to confirm that my script, so my Gaussian script, is executable, right? If it was not, I would type chmod 755 Gaussian.sh, and that would make it executable. And then to run, I just type /Gaussian.sh, and now I'm executing both of those files, and they should finish momentarily. They're both done now. I can list my G98 files. I have formaldehyde.g98 and I have hydroxylamine.g98. So now I can look. I can actually load both of these into gedit at the same time. It'll still look at it, so you have formaldehyde and then hydroxylamine's over here, right? And so, you know, this is our Gaussian. We go down to the bottom. We finish this in 6.4 seconds. I always like to read the quote. That's always fun. Never listen to criticism, or you'll be doing everyone else's thing, but your own. And then hydroxylamine is finished. We have 7.4 seconds, and here we have a quote by Richard Bach. The best way to pay for a lovely moment is to enjoy it, right? So now what I look at, I want to find a line up here. I want to look for the population analysis using SCF density, and I want these alpha occupied and virtual eigenvalues right here, right? So these are all my energies for all of the eigenvalues, and these are all in atomic units. And so the highest occupied orbital eigenvalue, that's this one, minus 0.26849. And now we want these in electron volts, or EV. So what is the conversion factor for between EV and atomic units? So 1 atomic unit of energy is 27.21 EV. And so I can just look at my calculator over here, and we will take 0.26849 negative times 27.21, and so that's minus 7.31, rounded off to 2 decimal places. So that's my highest occupied molecular orbital, and then my lowest, this is actually formaldehyde. So this is going to be attacked by the electron. So actually, in this case, I want the lowest unoccupied molecular orbital. So in this case, I'm going to actually look at the 0.04, 216, make that negative, multiply by 27.21, I get minus 1.147, minus 1.15 to 3 significant digits. So there's actually sufficient energy difference between the highest occupied and the lowest unoccupied molecular orbital. And so that kind of tells us this is a good candidate for our reaction right there. Now let's go over to hydroxylamine. Let's look at the same thing, but hydroxylamine is going to be, this is going to be doing the attacking, right? So here's our population analysis data. Here's our highest occupied molecular orbital, and then my lowest unoccupied is over here, right? In this case, I want the highest occupied molecular orbital because we want those electrons. These are what's going to attack the formaldehyde, right? So we're going to take minus 0.25449, like that, multiply by 27.21, and I get minus 6.92. So we have a good value that's sufficiently different from the LUMO of formaldehyde. We can also calculate the LUMO of this molecule just to look at that. So 0.08123 times 27.21, and I get 2.21. So a little bit lesser of a distance, but it's still a pretty good distance there. So that's how to find the HOMO and LUMO energy in Gaussian, and so then you can also calculate that 1 atomic unit or 1 Hartree is equal to 27.21 eV, right? Then what we want to do is we want to look at our checkpoint files. And so now Avogadro is going to read a formatted checkpoint file. So that's an fcheck file. So what I need to do is run the formcheck command to convert that to an fcheck file for both of these. And so we'll do that. Now I've got an fcheck file, and then in Avogadro, I bring up my Avogadro right here, and we will go to File, Open, Formaldehyde. Where's formaldehyde? That's right here. Here's my I want to load the fcheck file in Avogadro. So there's my formaldehyde, and then I'm going to go up to Analysis, Create Services, Create Surfaces, and I want to visualize the molecular orbital. And for formaldehyde, I want the LUMO. For hydroxylamine, I want the HOMO. But here I want the LUMO. I calculate, and let's take a look. And so what we see is that LUMO, that lowest molecular orbital, the largest point of this is right on the carbonyl carbon right there. So what that shows is that's an excellent candidate for nucleophilic attack by the hydroxylamine. So there's my molecular orbitals for formaldehyde. Now if I close that out, then we load Avogadro again, and we're going to go to Open. And this time I want hydroxylamine. We're going to open the fcheck file again. So here's my hydroxylamine. And so let's go to Analysis, Create Surfaces, Molecular Orbital, and this time I want the highest occupied molecular orbital. And where's that? There we go. So again, here's our molecular orbitals, the highest occupied molecular orbitals for hydroxylamine. And again, the largest ones are right there on the nitrogen. And so the nitrogen is going to be attacking the carbonyl carbon, and they're going to link together that way. So that's how the reaction goes. So that's how we calculate the molecular orbitals, and that illustrates frontier molecular orbital theory for formaldehyde. And so what did we learn today? First of all, I learned that frontier molecular orbital theory will predict reactivity. Secondly, we learned that HOMO and LUMO interactions control reaction mechanisms. And third, we learned that Gaussian 09 and Avogadro can help us calculate and visualize molecular orbitals. So if you found this useful, don't forget to like, comment, and subscribe to this video. Hit the little bell icon, and then you'll be notified of future topics that we're doing on here. And let me know in the comments about any other computational chemistry topics you'd like to see in the future or anything else. So I'll see you again, and don't forget to subscribe for more quantum chemistry deep dives we're doing on here. Have a nice day.